The segment of society we are focusing on is ground transportation, more specifically shortest path algorithm and traffic light optimization algorithm. Our first case study uses Dijkstra's algorithm. It is used extensively in Google Maps. Routes are discovered through an exhaustive search. A tentative route replaces a previously calculated one if the route is shorter.
We will use this example to demonstrate Dijkstra's shortest path algorithm. In this example, S will be the start node and F will be the destination node. We begin with initializing every node with a tentative distance value. The start node is initialized to 0, while all other nodes are given a value of infinity. Also, we have an unvisited set of nodes, which includes all nodes other than the start node S. On the first pass of the algorithm, we assign the current node to be the start node, which is S. We then consider all of S's unvisited neighbors. In this case, that would be A, B, and F. Looking at A, we compare A's previous value, which was infinity, to the path distance from S to A. In this case, 0 plus 1 is less than infinity, so we're going to assign A's new value to be 1. Using the same procedure, B is assigned a new value of 2, and F is assigned a new value of 10. We then remove the current node from the unvisited set. In this case, S was not in the unvisited set, so it remains unchanged. We now pick a new current node. To pick the new current node, we select an unvisited node with the lowest tentative distance. In this case, that would be A. We then look at all of A's unvisited neighbors. In this case, that is only F. We then compare F's old distance value, which is 10, to the new path distance from A, which would be 1 plus 4. Because 1 plus 4 is less than 10, F's new distance value becomes 5 instead of 10, and the unvisited set is updated to remove A from the unvisited set. We then assign a new current node. This time, the unvisited node with the lowest value would be B. We look at B's unvisited neighbors, which is only F. We compare F's old distance value of 5 to the new path distance from B to F, which is 2 plus 1. Because 2 plus 1 is lower than F, F is given a new tentative distance value of 3, and B is removed from the unvisited set. Now the current node would be F. F does not have any unvisited neighbors, so it terminates, and we return a value of 3 for the shortest path.
There are a few ways that Dijkstra's algorithm could be used negatively. It does not consider safety or traffic jams. Without Google Maps adding other software, Dijkstra's algorithm could send drivers into dangerous situations. Also, even though the total distance is less, the algorithm could send drivers down slower or more congested roads. The second case study considers SCAT's optimization. The study took place in Mashhad, the second largest city in Iran. It looked at the city's traffic problems. It compared various metrics measuring performance of SCATs and the standard fixed time control system. The study found that SCATs reduced the average vehicle's delay time by 9.23%.
Alright, so here's a visualization of 3 consecutive cycles in the SCATs algorithm. The SCATs algorithm is used to optimize traffic flow at an intersection. It starts off with a fixed time because it has no previous cycle to base it off of. In this example, we'll say that it allows roughly 3 cars to pass through the intersection, which is perfect because there's 3 cars here. However, there's 4 cars here, which you'll see in the next cycle. It couldn't get through, so it's still waiting in the queue here. Now it's optimized to allow 4 cars through because that's what it saw in the previous cycle. However, you'll see there's only 3 here and 1 here, so there's plenty of time that no cars are passing through, which you'll see in the next cycle allows red cars in the vertical lanes to stack up. Now it'll allow 3 cars through the intersection, but there's 5 in each of the blue lanes. In the next cycle, it'll continue to optimize to hopefully allow optimal traffic flow for the horizontal and vertical lanes.
There are a couple ways that SCATs could be used negatively. It does not consider the importance of a vehicle that may be stuck in traffic. For example, ambulances, fire services, police, etc. The algorithm also does not consider what other intersections lights are doing, so 2 intersections could be funneling traffic into a 3rd intersection, creating gridlock.